Hello friends, welcome to follow up. In this video, let's have a look at problem 606, construct string from binary tree. This problem actually has something to do with binary tree serialization. So there's one point we're going to emphasize, but the problem itself is rather straightforward. So our goal is to just starting from reading the requirements and then do the coding, and in between we're going to emphasize the point. So here we are given the root of a binary tree, so we want to construct a string consisting of parentheses and integers from a binary tree with the pre-order traversal way, and then return it. So we want to omit all the empty parentheses that do not affect the 1-1 mapping relationship between the string and the original binary tree. So here, if you look at the examples, you see here we have a tree. So especially you look at this subtree rooted at 2. So it has a left subtree, so 4, right? So here, but they do not have right subtree. So we don't need to include empty parentheses. So if you look at example 2, so these two trees are actually not the same. So here the subtree rooted at 2, it does not have left subtree, but it does have a right subtree. So, and if you look at the representation, so you get 2, and then you include the empty parentheses, which indicate that 4 is a right subtree. So this is an important point we're going to emphasize in the coding. So if we can realize this point, then writing the code would be rather straightforward. So this is the point we're going to coding and point out again. So here the constraints are the following. First, the number of nodes in the tree is in the range given by the closed interval 1 and 10 to the power 4. But notice here, this tree is not a null tree. But if we want to write a recursive solution, so we need to consider the case we are going to have a null tree. So here the node value is in between negative 1000 and a positive 1000. This is not that essential for us here. But if you have a lot of nodes, that's 10 to the power 4, and then you have this number of values, it means that some values must be repeated. So this is another point to observe. So with that said, we are ready to do the coding. So well, for the coding, tree is a recursive data structure. Therefore, we can consider recursion. So here, I'm going to use it as basic practice, right? It's so straightforward. So here I'm going to use recursion, but this problem is related to serialization, right? Here, the point we want to notice is that, so if you have a left subtree, let's see, I'm going to use 2. Let's see this subtree, we have 2, we have a left subtree, and then we are going to use this, right? 2, 4, right? Then you can make it a string. So that's one case. Another case is that you have 2, but you do not have left subtree, but you have 4 as right subtree. But in order to indicate that it does not have left subtree, or indicating 4 is a right subtree, we are going to need the empty parentheses. So that's a point to notice. So with that said, we are ready to do the coding. First, so I'm going to consider the stop condition or base case, more precisely the base case in the recursion. So in this case, I'm going to return empty string, right? So as I mentioned, though the tree as a whole is not a null tree, we need to write this stop condition or base case when we do recursion. So notice that we also need to think of the order. So here we need to do pre-order. So here, let me give a quick concept. So pre-order, right? So the pre-order is that you first visit a node, and then left subtree, and then right subtree, recursively, right? So if you think of pre-order traversal, so in example 1, what you are going to give is you have first visit the node 1, and then you look at the left subtree. For left subtree, again, you are going to visit the root first, and then you look at left subtree, that is 4, right subtree, null, right? Then after you finish the left subtree, you are going to look at right subtree, that is 3. So this for example 1. So now if you look at example 2, so you are going to get the same representation if you just for traversal, right? So now let's work it. So we first visit the root node, that is 1, right? Then we look at left subtree, we first visit the root again, that is 2. Then we look at left subtree, which is null. Then we look at 4. So we are going to get 1, 2, 4. Then if we finish the left subtree, we are going to look at the right subtree, that is 3. So we get 3. So you see that for both example 1 and example 2, their traversal gives the same list, right? So that's why we need to pay attention to the serialization or string representation. We need to distinguish these two situations, right? For this, you cannot distinguish, right? So now let's do this. First, we are going to consider if we do not have, we just have a single node tree. So if not root, let's rewrite with some redundancy, right? Not root left and not root right. So in this case, we just need to return the string corresponding to the integer in the root, right? So we're going to do string, so the root, so we can access its value attribute. Then if we consider the else block of this whole, then either we have a left subtree or we have a right subtree or both, right? So now let's consider if not root left, right? So in this case, we must have a root right subtree. So in this case, we need to pay attention, right? So we need to return string root value, and then we know we do not have left. We need to indicate, for example, here this is the right subtree. We need empty parentheses, so we do this, right? And then we do the string or the traversal for the corresponding right subtree, that is root right, right? But you know, we need to manually do something like this. So we do left parentheses plus this one, then plus right parentheses. So this is one case. And then other case, so we have if not root right, right? So in this case, what we are going to do, so we return same thing here, right? Then we do the representation for the left subtree. So here I'm going to copy this part and change the left attribute to be the left attribute. So left. But we don't need further empty parentheses because we know, because as long as it's next to the root representation for the root, it's going to be the left subtree. So this is the case. So in general, so we have both left subtree and the right subtree. What we're going to do, let me copy this part. I have left subtree, and then we also need to add the right subtree, right? So this is the part. Yeah, this forms a solution format, but I know that this writing is a little bit messy, but this way helps us to understand the logic. So now with that done, let's do a test. Yeah, it passes the first example. So now let's look at the second one, right? So we hope that we can distinguish these two situations. Yeah, it passes the second one. Now let's look at the generic case. Yeah, it passes all the cases. So that's basically about it for the coding part for this video. So here, let me emphasize 2 points. First is that though maybe you have some say traversal, here we have pre-auto traversal, then the result for the traversal might be the same, but it corresponds to different trees. In other words, different trees may have different traversal results, right? There's not a one-one correspondence. So this is the one thing. Another thing is that in this problem, if we use parentheses representation for the binary tree to do serialization, we need to distinguish using or not empty parentheses, or distinguishing left subtree and right subtree if they have the same node value. So with that said, I guess that's about it for this video. Thank you.